the last lesson in chapter 11. And after this, we're going to move on from confidence intervals to hypothesis testing. And we'll do kind of the same structure hypothesis testing for proportions and hypothesis testing for means. And then after that, we'll have a test. So, but that kind of means there are two big ideas in your test. There's confidence intervals and then there's hypothesis testing. Those are the two big ideas. And then you've got all the specifics about different situations. So today's lesson, make sure I have my eraser. There we go. Focuses on two population means, because we've done the one population mean and the mean of paired differences. So two population means. In this case, we have two populations instead of just one, or a before and after, where independent samples are available. And for your two populations, think like men, women, something like that. We're interested in comparing the means of the two groups of the population. For example, and I love talking about height, you know the tallest people in the world? You know what nation?
Oh, no.
No, not Sweden.
It's one of those.
It's also blonde-haired, blue-eyed nation. Dutch. What country is that? The Netherlands, where Amsterdam is. So Dutch people are apparently, if you go on a KLM flight, all the stewardesses are tall. So it's crazy. Compared to people who are Japanese, which tend to be, I think they're one of the shorter populations. Do you want to compare the average height of a Dutch person to the average height of a Japanese person and see if there really is any difference, just, for kicks. So in this case, we find the means of each group. So that would be x bar 1, or x1 bar, and x2 bar. And in general, try to make this first one the bigger one, if possible, because then you're going to result in confidence intervals that often have positive values instead of negative values. It's just easier. So pick x1 to be the one that's bigger, and your book will often specify which order you should go in. It doesn't actually matter, but once they say what order to go in, please just follow directions. And then compute their difference, which is x1 bar minus x2 bar. And then the way you find the standard error, because you also need standard error for confidence intervals, right? This formula, do you remember what this was? It's okay if you don't.
So S1 over X squared?
Very, very almost. It's S1 squared over N1 plus S2 squared over N2.
Both of the x's you put a 1.
Oh, yes, it should be a 1 and a 2. Thank you. And you can think if you only had one mean, that would take one of these guys away, right? And then you would get S1, because you could then square root it, divided by root N1, right? Okay. Find the degrees of freedom. Find the degrees of freedom. So we use an approximation of T star, where the n that we choose is the smaller of the two samples. Because there's no requirement that this sample size equals that sample size, and so just to be on the safe side, you choose the smaller n, and then that gives you kind of like a worst case scenario kind of thing. Okay? Awesome. Okay, using this confidence interval procedure will be valid if the population of measurements are both blank-shaped and random samples are measured. So probably bell-shaped. The observed data should not show any extreme skewness, and there should be no outliers. So if you have an outlier, try to have a good reason as to why that outlier is okay to not consider, hopefully. And it's also better to pick a bigger sample, and your book defines large samples to be n bigger than or equal to 30. But bigger is better as long as it's representative. Okay. So suppose that somebody found a confidence interval for the difference between two population means. What could you conclude about the population means if the interval did not cover 0? So you found a confidence interval for mu1 minus mu2. And just remember that if mu1 equals mu2, what is true about their differences? There's 0, right? Which means if these two means are the same, then 0 should be a plausible value for their difference. So if the interval does not cover 0, that means 0 is not a plausible value, right? So mu1 minus mu2 is not equal to 0, i.e. 0 not a plausible value. So you could conclude the means are actually different. Do you buy that? If you found your mean height of Dutch people minus mean height of Japanese people and did the difference and found a confidence interval and 0 is not in there, you're going to conclude that probably is the case that these heights are different. You could maybe even conclude it one way, that Dutch people are taller than Japanese people. Okay, what if the confidence interval did cover 0? Well, that means that 0 is a plausible value. And it's possible that mu1 minus mu2 equals 0, or mu1 equals mu2. You haven't ruled it out yet, so to speak. Other than the standard error formula, finding confidence intervals for this stuff is pretty similar to the last stuff. It's almost not different at all. So, should we do an example? I know you're so excited about this, right? Yes, it is. Okay, read the next one over and see if you can do part A. Because part A is pretty easy. Come on, try. Some of you are not reading.
It is Friday.
Anybody get A?
I think so.
2.2, yeah. So so we have 36 men with mean head circumference of 57.5, standard deviation of 2.4. 36 women and the mean head circumference of 55.3 centimeters with a standard deviation of 1.8. Find the value of the difference between the sample means for men and women. Why did they choose men minus women?
It's bigger.
Men's bigger? Okay, so this is, the notation would be x1 bar minus x2 bar. Does that make sense?
Yeah.
Okay, so an x1 bar is which of those numbers? 57.5 minus x2 bar, which is?
55.3.
And that comes out to be 2.2. Okay. All right, how about you do the next one, the standard error of the difference. That's just, what is the standard error formula?
I see what you're saying.
Almost, because we have two means. It's SE of x1, root,
Yeah.
You don't have to memorize these formulas, like it's not required of you, but I find that it's quite helpful to just write them down every single time I use them so I know what I've used. Does that make sense? And then you're going to end up memorizing them because you don't want to. So plug this in your calculator and see if you can actually get the right thing. No, I don't have one, so give you some time to work it out and we'll see. Anybody dare to say what they got?
0.05.
I got point I just got
0.5,
0.5.
sorry.
That's okay. Did anybody else get 0.5?
Yes.
Yeah, okay, great. Awesome. All right, part C says to find the confidence interval. So what is the only thing you're missing? Degrees of freedom, which tells you to find your T star, right? Okay. So for the degrees of freedom, you take the smaller of the two sample sizes minus 1. So, but they're both the same, right? So it'd be, I think it's 36 minus 1, which is 35. And 35 is not on your list, but 30 is, and so is 40, right?
So it's always over 3.
Let's use 2.03 in that case, since it's, an average of these two values. So T star is equal to 2.03. Otherwise, if you're not like at a halfway point, you could just, go with the less one or the bigger one. It doesn't really matter. They're so close together at that point in time, it's not gonna make that big of a difference. Okay, so then your 95% confidence interval is x1 bar minus x2 bar, like that value you found, plus or minus the T star times the standard error of x1 bar minus x2 bar. So basically same structure as before, right? So is that 2.2? Plus or minus 2.03 times 0.5. Okay. So what'd you guys get for the lower number?
1.185.
1.185, so that would be 1.19 if we run to two places, right? 2 on the high end,
3.2.
3.22 would it be? If you have more decimals than I asked, that's also fine. Let's just write one small little sentence. So with 95% confidence, men have a head circumference between 1.19 and 3.22 centimeters larger or than women. Does that make sense? Okay. So your book says this is okay to do, although I think it's probably better if you just use the actual numbers that are given in your table. But if you look at this table for the 95% confidence level, do you notice that when your n gets pretty big, as in like about at that 30 range, you start to get closer to that T star equal to 2? What this is saying is that when your sample sizes are at least 30, your T star gets close to the Z star, which is 2 for that case, right? You're technically 1.96. And so you can just use 2 for the multiplier, and it's pretty much good enough. So, and just look at this. A sample size of n equals 30 corresponds to what degrees of freedom? 29. And at your table, what would your T star be in this case?
2.05.
Which the basic idea is this is like close enough to just use 2. That's kind of what it's saying. Okay. So here we go. I keep talking about diet studies, and I'm sorry because that's the thing at the end as well. So I'm not obsessed, I swear. So a study comparing weight loss for 42 men put on a diet, and 47 men were assigned to exercise. And we're interested in which one of these things works better. Is exercise better or is diet better? And so the men who were on a diet lost 7.2 kilograms. And I know that we don't think in kilograms, but that's a lot of weight, right? 7.2 kilograms is like 15 pounds, approximately, right? It's a little bit more, I think. But what is that times 2.2? You can actually get exactly. Because I'm in Europe and I'm like, oh, 10 kilograms, no big deal. And then I'm like, wait a second, 10 kilograms. 15.84. The standard deviation of 3.7. And the men who exercised lost an average of 4 kilograms with a standard deviation of 3.9. And this is actually not abnormal. Diet does, for weight loss alone, work better than exercise. Like, it definitely has been observed in more than one study. Now, that doesn't say that they don't both work, but on average. So first, find the difference in means. Use diet minus exercise. So x1 bar minus x2 bar. And I boo-booed. I didn't mean that because I want positive numbers. Oh, no, that's right. Never mind. I didn't boo-boo. Diet was the larger weight loss, wasn't it? Mm-hmm. So 7.2 minus, so that's 3.2. Is that all right? Okay, the standard error. Standard error of x1 bar minus x2 bar is equal to root s1 squared over n1 plus s2 squared over n2. Be a little bit careful here that you put the right standard deviation with the right sample size, because this time the sample sizes are unequal. You see what I'm saying?
Yeah.
Okay, so what's the standard deviation corresponding to the diet group?
3.7.
Okay. Over, that's going to be,
Or 42.
yes. Plus,
3.9 squared. 40 squared.
which I got to be approximately 0.81. Make sure you can make your calculators do that too. Did you get the same thing, or are you still working?
Yeah, I got the same thing.
Okay. Alrighty. Find the confidence interval, good to go? Okay, find an approximate 95% confidence interval for the difference in these means. So x1 bar minus x2 bar plus or minus your t star times standard error of x1 bar minus x2 bar. So what was your x1 bar minus x2 bar?
3.2.
Plus or minus, and in this case, we have one sample size of 42. You have one sample size of 47.
Use 42.
Use 42. So our degrees of freedom will be 42 minus 1 or 41. Okay. So in this case, we could just go with 40, but since we're bigger than 30, let's just go ahead and say 2 for the multiplier. Times 0.81. So that's 3.2 plus or minus, what, 1.62? So what's 3.2 minus 1.62?
1.58.
1.58, okay. And then 2, 4.82?
Yeah.
Okay, and then one little sentence at the end. I know you don't have tons of space there, but squeeze it someplace. With 95% confidence, men on the diet lost between 1.58 and 4.82 kilograms more than whom?
Than men who exercise.
Than men who exercised. That might also mean that men exercise gain muscle too, right? This is also a possibility, but if you're just looking at weight loss, people on the diet lost more. Okay. So in general, I want you to use that standard error formula. There is another formula that kind of pools things together into one group. And you can do this when these groups have equal standard deviations, or approximately equal standard deviations, and then you just kind of are accounting for the difference in sample sizes that might occur. That's called the pooled standard error. And here is the formula for it. So sometimes it might be reasonable to assume populations actually have equal standard deviations. And since the variance describes the square of the standard deviations, these two variances will be equal. So what this formula does is gives you this pooled standard deviation to work with. Like first you find this because you kind of average the standard deviations between the two groups, but you've got to kind of average them based on sample sizes. Like one might have 50 and one might have 70 people in different groups. So you've got to account for that, and this gets an estimate. And then you find the standard error of x1 bar minus x2 bar is equal to the root of, and you plug in this value, sp squared over n1 plus sp squared over n2. So that's the pooled version, where you first find the sort of average of the two standard deviations, versus the other one, the unpooled one, and so what this does to your life, at least for the next homework assignment, is you have to just do one more step. You've got to kind of find this thing that kind of is like the average of the standard deviations. And then you use that average standard deviation to find the standard error. It just adds one more step. And the directions will say to do this. Okay, they will indicate that you need to use the pooled standard deviation. And I think there's even one homework problem where it has you do it both ways. And from what I can tell in the problems you're given, the results aren't drastically different, and I'm not really sure why it matters. But I think there really is a theoretical basis for this thing. So you just have to kind of know that it exists and think it's kind of like averaging the standard deviations together. That's the basic idea. And then that's the confidence interval thing. And the one nice thing about this is because you assume those standard deviations are the same, it lets you put the degrees of freedom together into one thing instead of just taking the smaller of the two. And one nice thing about that is you can have two groups together makes a bigger group overall, right? Now the one difference is you now use the first degrees of freedom, which kind of is like n1 minus 1, plus the seconds, which is n2 minus 1. That's why this one is minus 2 instead of minus 1. We'll actually do stuff later in this class where we have like 10 degrees of freedom in our example. And that will change, things. Okay. All right, ready to try an example? Okay. All righty. So let's revisit the zinc thing. So we're going to do this two ways, both the unpooled and the pooled way. So find a 95% confidence interval for the difference in means for the two groups. We're going to use placebo minus zinc. We're going to use the unpooled procedure to start. So this one didn't number the steps, but first thing you should do is find the difference in means, which in this case is x1 bar minus x2 bar. And I think if you've been in class, you've seen this example repeatedly, right? Okay, so we said placebo first. So what was the placebo's average length of cold?
8.1.
Minus the zinc's.
4.5.
Yep. For a difference of 3.6. Next thing, find the unpooled standard error. So that's the formula that we've been using. which is S1 squared over N1 is S2 squared over N2. So what's S1?
1.6.
1.8.
It doesn't actually matter what order here, but sure, we'll stick to the same order. 1.8 squared over
23.
Plus
1.6 squared over
25. If you did mix those up, it wouldn't matter, though. Does that make sense? Why?
yeah.
Because when you add, the order is irrelevant, yes? Okay. So this should come out to be 0.49. Tell me if you also get that. Anybody else get that? Or it's not there yet?
0.493.
0.49 what?
0.493.
Okay, so 0.49 is good then?
Yeah.
Okay.
Yeah.
Awesome. Okay, so then find your confidence interval. Pretty much, oh, we do need the T star, don't we?
Yeah.
So T star, we look at n equal to 23, which implies our degrees of freedom is 22. Exactly. 2.07, yep. So T star equals 2.07. So we have 3.6 plus or minus 0.49, 2.07. Well, it doesn't matter.
It doesn't.
It doesn't matter because multiplication, yep, yep, exactly. So on mine, I got, sorry, I made a right O. What's 0.49 times 2.07? 1.01? Yeah, so I got 2.59 to 4.61. Does that seem legit? Okay. And because I know you have space, let's write one little sentence about that. With 95% confidence, the average length of cold is 2.59 to 4.61 days longer on what?
Placebo.
On the placebo. Or you could say that the people taking zinc have cold lengths that are between 2.59 and 4.61 days shorter. That's the exact same thing. Okay, are we ready to move on to the next part? Yes? No? Good, okay, yeah. I like when people give me hand signals. Okay, so repeat part A using this pooled procedure. So certain parts don't change. Does the mean change? No. So we still have x1 bar minus x2 bar is equal to 3.6. That's not different. What we have to do now is we have to get this pooled standard deviation thing. And so the formula for that, which I know that you're not going to memorize, and nor do I want you to, is n1 minus 1 times s1 squared plus n2 minus 1 times s2 squared over n1 plus n2 minus 2. So tell me what to plug in where, and then we'll have you do the calculation in your calculator. So what goes in for N1?
3.
No, I think
20.
we've got the zinc group first, right?
So 25.
Our group 1 is zinc.
So 25.
It'd be 25, although I think it might not matter. 25 minus 1 times, that group had a standard deviation of 1.6, right? Plus 23 minus 1 times that group standard deviation was
1.8.
divided by 25 plus 23 minus 2. So does it appear that the order mattered? No, it didn't. Now, when you're putting this in a calculator, you have to be very careful with how you put parentheses. Because if you don't put parentheses around your denominator, it's only going to put the first number in the bottom. If you want them all in the bottom, parentheses there and there. Okay, so like right there, right there. And the same thing for the numerator. To keep it all on the top, add in parentheses there. So with whatever calculator you love to use, try to punch this in and see if you can get it to work, okay? I'll give you a few seconds
All
just.
at once?
Calculators can do this all at once if they're smart enough.
Anything else?
Yours actually is smart enough, I think. Let me do something. Let's trade and I'll try. I think I have my calculator with me. You use the little pinky. Pinky's a cool calculator. It's got that funny square root. Maybe you can't do the square root first, but we'll see about it.
I have 5.66.
I got, did you square root it yet?
Yeah.
Because I got 1.6986.
That's what I got.
Yeah, okay.
I don't know what I did wrong.
I don't know either. Yeah, I don't like this calculator. Mine's way better. Keep using it, okay? Because this is superior. So you should get before I rounded, I got 1.6986. Which if you're going to round to like even, well, let's round to 3 decimal places. It's about 1.699, right? Yes? Or, well, whatever. Okay. 1.7. You okay with this?
No, I was like,
Okay.
I just did something really stupid.
Okay. I won't judge. I make dumb mistakes all the time.
Well, not the same answer, but I just missed a step, and then I figured out why I missed the step.
Good. Okay, spectacular. Now, the problem is that this is still not your standard error yet. Okay, so the next thing you need to do is you need to get the pooled standard error of x1 bar. And to ease the pain, think about summer swimming pools. Okay, no one likes that joke. All right, I won't use that one again.
Because it's not summer.
SP squared over N1 plus SP squared over N2. I forget who watches Doctor Who besides me.
Don't watch this show.
Don't watch that show, you should. Feels like when Matt Smith says, "Who the man?" and then he says, "I'm never gonna say it again." Yeah, that's what I feel like all the time. Okay, so moving on. Root 1.7 squared over 25 plus 1.7 squared over.
22.
And it kind of makes me mad the only example they give you, this comes out to also be 0.49. Not really any different than the other one, right?
It's just a longer process.
It's a longer process, but the nice thing about this, and I think that really the point of this is to allow yourself to have bigger degrees of freedom. Guys, so I think that really is the purpose of this procedure, because now, when you're looking for your T star, you use degrees of freedom equal to N1 plus N2 minus 2. And having bigger degrees of freedom means what happens to your multiplier? It goes down, it gets smaller, which makes your interval narrow, which is a good thing. So our degrees of freedom in this case, what's the N1? 25 plus 23 minus 2 gives us 46. And at that stage, can we use a better multiplier? We could use T star equal to, yeah, or we could just, well, you can just say T star is 2, right? Yeah, but you could have also gone with like half of between 40 and 50 and used 2.01, but the point is you're bigger than 30, so go ahead and just use 2. And so then the confidence interval is 3.6 plus or minus 0.49 times 2, which is 3.6 plus or minus what, 0.98? Or 2.62 to 4.58. I think this would be particularly important if your sample sizes were a little bit smaller, like you had like both N1 and N2 equal to say like 11 or something like that. I think that would make a much bigger difference in terms of like the confidence interval sizes relative to each other. So on your homework, if you do these examples and you get things that are not very different, don't freak out. Isn't that nicer? Yeah, you don't.
I need to figure out how to use it.
Yeah, of course. Okay. All right. So last question is to compare the unrolled, whoopsies, unpooled, oh my goodness. Back when I was a college senior going into graduate school, I had to write a paper for the National Science Foundation, and I kept punching in 2 S's when I tried to write as. Repeatedly. So bad. Folks, I couldn't catch that one. So compare it, and I had a really nerdy guy reading my paper, and he was like, "You did it again." So compare the unpooled and pooled results and discuss which procedure is more appropriate. So the pooling here is kind of like taking these standard deviations and kind of averaging them into one. And so it's an appropriate thing to do if your standard deviations are pretty close together. And so in this case, were the standard deviations pretty close together?
Yeah.
Yes. So we could say that since S1 and S2 were nearly the same, the pooled procedure makes sense. Or we'll just say is more appropriate. And the benefit there is it gets you bigger degrees of freedom. If that S1 and S2 were not close together, then it probably would not be an appropriate procedure to apply. So. Okay. This one is gross because you have to find the mean and standard deviations for each group. And I guess I didn't actually do the whole confidence interval findings. We've done so many. I think once you have the mean and standard deviation, you can do the confidence intervals, right? You buy that? Okay. So you're looking at the pulse rates for 20 people based on if they do or do not work out. And it is true that on average, people who exercise have lower resting heart rates, right? My GPS tells me mine for today. Oh no, that's the wrong mode. Go away. Save. Yeah. Gives me a graph, which makes the mathematician in me so happy. 56 for the day. That's mine. Okay, moving on from my egocentric stuff. So we have 2 groups, the yes group and the no group. So you want to find the mean and standard deviation of both of them. So first of all, how many yeses are there? 2, 3, 4, 5, 6,
13.
7, 8. Yeah, nothing said they were equal. And all these guys, right? Okay. I think there are 12, yep. So x1 bar is going to equal 62 plus 72 plus 60 plus 63 plus 75, 64, 60, 52, 64, random person with a resting heart rate of 80, holy moly, 68 and 64. Divided by 12. If you feel like it, you could put these, and I think you should, put these numbers like into a thing like Excel and ask it to find the mean. I'm pretty sure if you do like equals mean and you select like a column of numbers, it will calculate it for you. Okay, so you're welcome to use that for something that as big as this because the same thing is true for standard deviation. I'm asking this question to see if you could use your computer if you had to, because in real life that will happen, right? Okay. Mean of a column, like in Excel. This should come out to be 65.3. And your X2 bar is all the other ones, right? So which numbers are we adding up there?
70,
Mm-hmm.
84,
Mm-hmm.
66,
Mm-hmm.
72,
Mm-hmm.
62,
Mm-hmm.
84,
Mm-hmm.
76, and 60.
Divided by, in this case,
8.
which comes out to be 72. There's the mean. Okay. Now, I don't want you to do the whole long standard deviation formula by hand, okay? That is not my point with this problem, so please don't do it that way. I'm going to be checking your answers for correctness, which means I want you to somehow use technology to get me a standard deviation for these guys, okay? So in Excel, here's what you do. You put in a little equal sign, and the command is STDEV. And then, if you have a column listed, you could just like select that column, I'm pretty sure. Or if you don't want to do that, you can put things in with commas. 62, 72, 60, all the way down to your last number, which is 64. And what it might help to do is do this with a friend who's sitting next to you doing the exact same calculation, kind of like read the numbers out as you put them in and then check against each other because it's so easy to miss one, right? And I got this to be 7.49. That's my first standard deviation. And the second one, also you put in STDEV, and like you need that equal sign in Excel to tell it to do a formula. And then your list would be the 72, the 84, down to the 60, and Excel gave me 9.13 for S2. So my point with those problems in your homework is just to, I'd like you to have a little bit of working familiarity with some technology because that does actually matter a lot in statistics. So use technology to do the standard deviation. And from now on, if you have a homework question and you want to check your answer, you can also use that. Just make sure you also know the formula in case I ask you one on a test. Because I will not give you computers on tests, no way, Jose. You can Google everything that way. Okay, so you were right with that? Okay, and the last thing is just something that's kind of fun for me because this is why I got interested in statistics. I read a book called Why We Get Fat and What to Do About It. And it talked about how all this statistics was done really badly in the health sciences, in particular diet. And this is one of the studies that they cited in that book, which you could go read if you feel like it, but anyhow. So it was it's an abstract for a Stanford study comparing weight loss among 4 different diets. If you want to go read the abstract where I found it, that's the link, okay? And I think that the article exists elsewhere, and there's YouTube videos, people talking about this article. So here's the context. Popular diets, particularly those low in carbohydrates, have challenged current recommendations advising a low-fat, high-carbohydrate diet for weight loss. Potential benefits and risks have not been tested adequately. So back when I was younger, like in early 2000s, like the low-fat diet was so like highly regarded that people were like labeling their candy as low-fat. As in like the fact that Sour Patch Kids has no fat was somehow making them good for you. Okay, that's what was happening back then, okay? And there's all these like horrible no-fat foods that existed. So here's their objective. They wanted to compare 4 weight loss diets that represented a spectrum of different diets, and they want to also measure related metabolic variables like what's your cholesterol, stuff like that, okay? And here's what they did. They had a 12-month randomized trial, and they had 311 free living overweight obese, so their BMIs between 27 and 40, which if you know body mass index is high, mine is like 23, just for a reference point. And these were all women. So participants were assigned to follow one of 4 diets, the Atkins, the Zone, the Learn or the Ornish diet. And also the sample sizes, you see they're reasonably good, right? Okay. And one thing also to note is that these women were not put in the metabolic ward. They were just kind of told what to eat and trusted to do that themselves. Which in terms of that's real life, right? So if you're going to talk about how effective is a diet in real life, you got to be able to kind of do that. So they received weekly instruction for 2 months, then an additional 10-month follow-up to see how they were able to do once they didn't have all that instruction, okay? And here are the results. So weight loss was greater for women in the Atkins diet group compared to the other diet groups at 12 months. And mean 12-month weight loss was significantly different between Atkins and Zone diet. So those two in particular were different. So here are the confidence intervals. So on the Atkins diet, they went with negative numbers. So what do you think negative 4.7 means?
You lost that much?
That's how much you lost. Okay, that they did after minus before. So negatives are weight loss. And the confidence interval that they have, this is also in kilograms. So 4.7 pounds is approximately 4.7 kilograms is approximately 10 pounds. So average weight of 10 pounds, and the confidence interval was negative 6.3 to negative 3.1. For the Learn diet, or for the Zone diet, it was negative 2.8 to negative 0.4. Notice that those two intervals don't overlap, which is how they could conclude that there was a significant difference between Atkins and Zone. Okay? But they didn't say it for the others because the others have a little bit of overlap, right? Negative 3.8 to 1.3. So there are a teensy bit of overlap there. And the Ornish was minus 3.6 to 0.8. So also they couldn't conclude that they were very different because there was some overlap. But anybody looking at those intervals can see that there isn't all that much, right? But the kind of interesting thing was from this study was that the Atkins diet did a lot better than the others. And you can read this in the abstract if you want to. This is just the weight loss results. The Atkins diet did also do better in all the metabolic ones. They had better cholesterol as well, which is not what you've been told is conventional wisdom, probably. So that's my real life study that used confidence intervals. A little bit neat. So.